Alright nerds, today you're going to learn the last brand new logarithm knowledge. Because everything after that last bit of knowledge is just using the logarithms. And this is my most important logarithm knowledge. It's knowledge I've been holding on to for the entire chapter so far. And we'll get to the punchline of that in just a moment. This section I'm calling the common and natural logarithms. I've combined section 8.3 and 8.4 into one because they don't need to be separated. So here's what's up. Mathematicians try to write as little as possible. That's just how it's always been. I'll call it laziness every now and then, but in all reality, it's just because there's so much writing in mathematics. So we're trying to write as little symbols as possible. Case in point, square root doesn't ever have the index written, even though we all know it's a 2. But for cube root, fourth root, fifth root, we put that index over the radical, right? But for square root, we don't. Okay, that's one of those things where the mathematicians are just trying to write less. On your calculator, you have a button that says log, but it does not have a base. In fact, every time you've seen me evaluate a log base, I did it with the graphing calculator because it does have a log base command, but the scientific doesn't. So does that mean there's no way for you to figure out what log base 2 of 3 is on the scientific? Of course there is. You just needed the last property. And I was holding on to that last property, and that's why you don't know how to do it yet. But that button on your calculator that says log doesn't have a base because it is the common logarithm. In fact, it's the most common logarithm. We call it the common log. It's base 10. So if you see log and there's no base written, it's automatically base 10, which is why there's a 10 to the x written right above it, because that is its inverse operation. Log base 10 is canceled by exponential base 10. So it is the common logarithm. We call it that because our entire number system is base 10. If you think about it, in elementary school, we teach you to talk about the place value, the ones, the tens, the hundreds, the thousands, the tenths, the hundredths, the thousandths. Those are all powers of 10. Our entire number system is base 10. Like the number 25. The number 25 is literally 2, 10 to the ones, and 5, 10 to the zeros. Our entire number system is base 10. And because of that, log base 10 is the most common logarithm that we mess with. So mathematicians a long time ago were like, hey guys, since we know it's always log base 10, can we just stop writing base 10 and we'll just know that's what it means? And they all just kind of said yes. But other than that, it's not special. It has no special qualities. Log base 10 of 1 is still 0 because log base b of 1 is 0. Log base 10 of 10 is 1 because log base b of b is 1. Log base 10 cancels exponential base 10, and exponential base 10 cancels log base 10. It's not special at all. Cool with that? All the expansion rules are the same. All of the condensing rules are the same. All of the solving skills are the same. Argument has the same rules. I mean, it's all the same. It's just base 10, and we don't write it. Comfortable with that idea? Okay. There's a whole section of your textbook devoted to just that. Waste of time. The other one, which is like the second most common logarithm, maybe third, I don't know, log base 2 is really common, is the natural log. That would be the ln button. And you see how written right above ln in white paint is e to the x? ln is not even its own symbol. It's literally shorthand. Stands for log of the natural base, because e is known as the natural base e. So ln is shorthand. It means log base e, log of natural base. And mathematicians just got sick of writing log base e. So they just said, hey guys, can we just agree that if I had log base e, I could just say log of the natural and just do that? And they go, yeah, we could do that. And you go, okay, great. So that's what ln is. It's literally log base e. And we're just being lazy and writing less letters. 2 letters instead of 4. But it's a logarithm. It follows all the same rules. Log base e of 1 equals 0. Log base e of e is 1. Log base e cancels exponential base e, and exponential base e cancels log base e. Now you'll notice I said log base e for every one of these ln's, for every one of these natural logs. I won't keep doing that. It's up to you to know that ln means log base e. Okay? But there's nothing special about it other than its name. It follows all the same condensing, expanding, solving, argument rules that every logarithm follows. So that's actually not even new. It's just a new symbol. You just didn't know what it meant. I could have easily been giving you guys questions that said log base e in them, and you would have had no idea that we were doing something special. Because you're really not. Okay. So let's go review some old skills. How about taking them out of logarithmic format and getting them into exponential format using the inverse properties? You know, that exponential bases cancel the matching log bases. I know it's not written, but this is log base 10. Hey class, what cancels log base 10? Exponential base 10 will do it. So what you're going to do is you're going to put base 10 underneath both the left and right sides. And now we have 1,000 is 10 to the third. Very simple. That's it. The next one tells us that the natural log of 2, the ln of 2, is approximately 0.693. It's not perfect. It's rounded. But remember, ln is log base e. So class, what cancels log base e? Exponential base e. We cancel the natural log, we cancel ln with base e. So we say base e on both sides. On the left side, those guys cancel. And we are left with 2 is what you get if you raise e to the 0.693-ish. You get about 2, something like that. Remember, it is rounded. That's not a new skill. It's just a new look, but not a new skill. And if I need you to be able to go from log to exponent, you know you should be able to go from exponential to logarithmic. Same skill sets, just new bases. Hey class, what's going to cancel a exponential base 10? Log base 10, but you know what? I'm not going to write the base 10. We're just going to know that if we write log, it means log base 10. So we're going to find the log of both sides. I'm going to show one extra step on this one. Are the parentheses required? No. Just a 10,000 is just a long number, so I don't know. Feels like it needs help being held to the logarithm in my mind. That's it. And the number e, which is like, what, 2.718-ish? It's a little bit less than 3. So if you raise a number that's less than 3 to the third, you expect a number that's less than 27. And that's what you get. E to the third is 20.086-ish. It's rounded. But what am I going to use to cancel? We can get lazy here, class. What cancels e? ln, the natural log. Log base e, but it's just ln. I write my natural logs with a cursive L. That way it doesn't look like in. You don't need to. I'm just letting you know that's what you're seeing here. Okay. So I'll use the natural log of both sides. It's a habit I picked up from math teachers along the way. So 3 is approximately the natural log of 20.086. Again, parentheses not necessary. You can write them if you want to. It really doesn't matter if they're there or not. Yes, sir.
The symbol means approximately, right?
Yeah, it's like that means I rounded it. It's not like if you don't use it on a test or anything, I don't really care. I just wanted to be really picky with myself. And since the common log and the natural log are just logarithms, they have no special rules. They follow the same rule set that all logarithms follow. We can expand and condense them. So once again, older skill set here. And we're just getting to practice it again, but with new bases. Yay! So like this one, we have a fraction in the argument of this logarithm. That means I'm going to get to set that up as the difference between two logarithms. So I have log of x squared, and then that red fraction bar is this red minus sign, log of yz. There is an exponent in the argument here, so that 2 can move to the front as a multiplier. So we have 2 log of x minus. Now, if there was nothing in front of it, this would be log y plus log z. But there's a number in front. So we have to make sure that both that log y and that log z get that number. Now, that number happens to be a -1. That is why it's actually log y minus log z. And then I think I told you guys the shortcut is basically, if it came out of the denominator of the argument, that logarithm has a minus sign in front of it when you're expanding. And when you're condensing, same rule set. If a logarithm has a minus sign in front of it, that argument will end up in the denominator when you condense. Okay. So bottom things, negative logs. Cool? But that's it. It's not a new skill set. Old skill set, new base. Yes, Barry.
Is it just pronounced like log of x?
Yes, log of x. You don't have to say log base 10 of x. You could. Or you could just say log of x.
And then for the natural one, is it just like ln of 0 to 6?
Yeah, we just say ln of. Yep.
Okay.
Or you can say the natural log of. But that means the same thing. And let's be really clear here. This doesn't have a base. It is log base e. But ln is just ln. Okay? I had a student a couple years ago that every time I said ln, he was like, and that's got a base e we're not writing, correct? And I was like, no, it does not have a base e we're not writing. ln does not have a base. ln means log of the natural base, which means it's log base e, but this does not have a... It's not like the common log where there is a 10 there, we're just not writing it. You see what I'm saying? The difference between the two? Okay. This is this. But we're just being lazy. Yeah. Okay. Here, condensing. We cannot condense logarithms when there are numbers in front of them. The only acceptable number would be a negative sign because that acts as a -1. That's the only acceptable number. Every other number that sits in front of a logarithm needs to be moved to the exponent of the argument. So the 5 goes above the x, the 2 goes above the y, the 3 goes above the z. Yeah, there's a 5 right there. Only one of these logarithms has a minus sign in front of it. So yes, there will be a fraction in the argument, but when I build this fraction, the argument of this logarithm will be the only thing we find in the denominator. The other two logarithms are positive logarithms. So it's almost as if we just go, well, if that wasn't there, we would just see, oh, the ln of x to the 5th plus the ln of z to the 3rd. And we'd multiply those two arguments. And then we divide them by what's left over. So there's a single logarithm now, fraction bar. The only thing that goes in the denominator is y squared, because this was the only negative logarithm. The other two things belong in the numerator with multiplication between them. Now, earlier today, I had a student ask a question that I'm surprised it took this long to be asked, but it's cool. Asked, what about logarithms that have addition or subtraction in their argument? Can we do anything with that? For example, is there a way to expand this? Well, the answer is no. You can't do anything with that, unfortunately. This does not expand in any way. There's nothing you can do with it. can be manipulated to be equal to anything else that's actually useful. I mean, you can manipulate it and have powers that have logarithms and stuff in them, or bases that have logarithms in them, but that's not useful at all. There's no nice things that can be done with addition or subtraction, unfortunately. Unfortunately. Yes, sir?
For the answer, do you have to have the multiplication dot?
No, the multiplication dot? No. You could have just written the x to the fifth, z to the third next to each other. I just put it there because I said they were multiplied. But yeah, no, it's not necessary. Ilya, what's up?
Is there a way to make the exponents condense more for the x and z?
I would say no, because the 5 and the 3 don't have anything in common. If they had a common factor, you could wrap an x and a z in a set of parentheses with an exponent on the outside, but since they have no factors in common, I would say no. Now, if this was, say, an x to the 6th, then I'd say, yeah, you could say this is x squared z in a set of parentheses, and the parentheses have an exponent on them, but you would never need to. I'm not going to make you do that. Other questions, guys? Is it good? We keep them up? Yes, Barry, what's up?
Could you condense it even more if x, y, and z has the same base?
When you say the same base, do you mean like if they weren't x, y, and z, if they were just all x, x, and x?
Yeah.
Well, yeah. Then you would have to use your exponent rules on the inside. Let's just say that all three of them were x's, right? You'd have x to the 8 over x squared, so you get x to the 6th. If they were all the same base, absolutely. If they're the same base, once you condense your logarithms, then you are allowed to use your exponent rules. 100%. Yes?
So if they were all like x to the fifth, z to the fifth, y to the fifth, could you do anything?
If all of them had the same power,
Yeah.
then you could do x, z, y, and then with parentheses around the argument, and just put a 5 on the outside of the parentheses if you wanted to. Yep. And then when you'd expand that, all three of the logarithms would have a 5 in front of them. Well, this one would have been a negative 5, but yeah. So we're going to go back to a question like this that was from section 8.1, the first day that I introduced logarithms. And I taught you how to cancel exponential bases by hand using an appropriate log base. Now, though, I actually want to know a numeric answer. I don't want an answer with a logarithm in it. I want a decimal answer this time. And we can pull that off by using either the common or the natural logarithm instead of a log with a matching base. But we don't want to get ahead of ourselves here. I'm trying to get x alone. What's the very first thing I'm going to need to do? Someone, what is that? Add 4. Cool. Let's add a 4 to both sides. Good old sad MEP, right? So we have 3 times 2 to the x equals 9. I'm hoping everybody in the room knows next operation what we need to do. Yep. Hopefully lots of people know and not just one or two. You guys don't need to be depending on those 1 or 2 people. You're all welcome to engage in the notes today. But yeah, we're going to divide both sides by 3. That is going to get me 2 to the x equals 3. In section 8.1, we would have isolated this x using log base 2 of both sides. And a very acceptable answer would be log base 2 of 3. But what does log base 2 of 3 equal? What if I wanted a decimal approximation? How would we get it? Because you don't know how to do log base 2 of 3 on this calculator. The answer is either use the common log or the natural log. And it actually doesn't matter. First come, first serve. Natural or common? Okay, common log. Every period today said the same thing. We'll use the common log here to solve for x. Take log of both sides. Now the common log is not going to cancel exponential base 2. It's not. But what it will allow us to do is expand this logarithm, because this logarithm has an x in its exponent position. So you could take the exponent outside of the logarithm. Log of 2 is a number. And anytime you have a number stuck next to an x and you need to isolate x, you divide. Our solution then is log of 3 divided by log of 2, and we can type that on our calculator. Make sure you close your argument though. Otherwise the calculator won't know when the logarithm is finished. And you're going to give it about 1.585. And I told you first come, first serve. I told you it wouldn't matter which one you choose, the natural log or the common log, right? Right here in red, had you said natural log, these would have both said ln. But I still would have had an x in the exponent position. I could have then moved the x in front of the natural log of 2, and it would have been equal to the natural log of 3. I then would have done divide by natural log of 2, and I would have had ln 3 over ln 2. The exact same answer. So does that mean that log of 3 is equal to the ln of 3? See, log of 3 is 0.477. ln of 3 is not 0.477. So is it magic? No. It's actually got a really easy explanation as to why that's occurring. Can we all agree that 1 divided by 2 is the same as 2 divided by 4? We can, right? But the numerators are 1 and 2. They're not equal, are they? So just because the two divisions give us the same answer does not mean that the pieces of the fractions are equal to each other. It just means they're in the same ratio. Okay? Now this one, we could use either the common log or the natural log. But because this one has an e in it, it makes a lot more sense, and it's actually a lot less work. Well, it's less work. I don't know about a lot less work, but it's less work to just go ahead and use the inverse of exponential base e. That's the natural log. But not yet. Like every other structure in mathematics, I can't cancel e until it's alone. So what do I need to do first? Lots of people, just tell me. Subtract. Yeah, I got to subtract that 5 from both sides. I have negative 2 e to the 3x equals negative 12. Lots of people, what's next? Yeah, divide. Divide both sides by negative 2. E to the 3x equals 6. Now, like I said, we could, if we wanted to, use log of both sides. And that would be fine. You would have an exponent in your argument. You'd move that 3x to the front, and you would have 3x log of e, not base e. Log of e equals log of 6. Then you'd have to divide both sides by log of e, and then you'd have to isolate your x. So you create extra steps for yourself. It makes a lot more sense right here to cancel exponential base e with the natural log. Take the ln of both sides. Allow ln and e to cancel each other out. You now have 3x equals the ln of 6, and x is alone if you divide both sides by 3. Now I don't know what that equals. I have to grab a calculator. ln of 6, make sure you close your argument. If you don't close your argument, your calculator will think that it's the natural log of 6 divided by 3, which is ln of 2. So you have to close the argument. There we go. 0.597. To 3 decimals. Yep.
Wait, so how did you know to put ln6 over 3?
You mean right here?
No, slightly below that. Yeah. Yeah.
Well, because it just said 3 times x is this number. So I had to get x alone. I had to cancel the multiplication between the 3 and the x. So use division. And you can't divide the argument because natural log, think of it as an exponent. So if you're doing PEMDAS, your exponents would happen before you did division. What do you guys think about solving exponential equations without using the appropriate log base? Well, I mean, this one you use the appropriate log base, but you don't have to. You can use whichever log base you want. Which is kind of interesting, isn't it? No? Just me? I'm the only log nerd? Okay, fine. If I can solve exponential equations, I can solve logarithmic equations as well. I can't cancel a logarithm until it's alone, though. What do we do? Say that louder, I didn't hear. Condense. You have to condense this to a single logarithm. This is me adding two logarithms with the same base. They're both log base 10. I haven't written in much red. I guess I'll write this one in red. There. Now the logarithm is alone. Now the logarithm can be canceled. What exponential base do I need to use? Lots of people, do we know that? What cancels log base 10? Exponential base 10. Okay. I know that the base 10 isn't written. It's our job to know it. You know what it's not allowed to be? A 1. And even though I've said that, I'm still going to have some students that think when the log base isn't written that the base is a 1. One of the rules of the base of a logarithm is that it must not be 1. Can't be 1. Okay. Anyway, let's use exponential base 10 on both sides like so. Let these guys cancel each other. And I now have x times x plus 21 equals 10 squared, but 10 squared is 100. Distribute your x. You get x squared plus 21x. That's a quadratic. If you have a quadratic, you need to bring everything to one side and hopefully solve by factoring. Luckily, I designed this question to yes, you can solve it by factoring. Yes, Ilya?
25 and 4? Or negative
25 and negative 4. Yep, because you have to multiply to negative 100. So we have x plus 25 and x minus 4. We have two solutions. Woot. We have x equals negative 25 and x equals 4. So once again, get out of here. Not new math, a new base. But that's it. I haven't changed anything. What do you think? Calm, cool, collected? Ready to move on? No. Thomas?
Don't we have to test them?
We have to make sure that our answers have not broken the rules of the argument. Remember, the argument of a logarithm cannot be 0 or negative. It must be a positive argument. Negative answers are allowed as long as they don't make the argument negative. But if I try to put a negative 25 right here, that gets me a negative argument. I mean, heck, it gets me a negative argument here too. But either way, you cannot use x equals negative 25. It is an extraneous solution. X equals 4 works just fine though. Please always check your logarithm answers to make sure they're allowed. Remember, I can write a log equation that has 2 answers, 1 answer, or no answers. You've seen them all. Between the notes and the homework, you've seen all 3 things occur. The next question does not have us doing any condensing at all. It's just straightforward, solve for x. Lots of voices, class. What do I do first? Yeah. I got some people talking to me. Yeah, we're going to subtract 6. Lots of voices. What now?
Divide by 2.
Yeah. Divide by 2. Class, what cancels ln? E. Specifically, though, base E. Exponential base E. It is important that you write it down and to the left. If you write it in front of ln, and you go to an AP class or an IB class, you will be counted as wrong, even if you get the right answer, because the way we write it matters. So it's exponential base E. Drop that bad boy down here. On the left side, base E and ln cancel. We get 3x equals e squared. And I think it's obvious. Just divide. We get our answer to be e squared divided by 3. I don't know what that is. My calculator does, though. Second ln squared, close the exponent, divide by 3. Let me remind you, on the other calculator, the battery-operated one, you have to type the argument of the logarithms first. You have to type the exponent of the e first. 2.463. Yes, Ilya?
Would you be able to solve it on the gray calculator? Or the battery powered?
Yeah. So you would, still do the divide by your minus 6, right? You'd have 4, divide by 2. And then once you did that, you would already have the number 2 on your screen. Then you would just do second ln. And it would evaluate e raised to the second power for you. Then you would just hit divide by 3. Okay. What do you guys think? Not too bad? Okay. Here I have my own brainchild. This is not in your textbook. This is a little bit of, I don't know, I've been calling it like math poetry all day. This is like a whole, coming back to where we started from situation. I don't know if you can remember this, but the very first thing that was written at the top of your 8.1 notes was, how do we solve 2 to the x equals 6? To the left, I had 2 to the x equals 4. To the right, I had 2 to the x equals 8. And then I asked, how do we get this x by itself? On that first day, I revealed to you that we could just use a log base 2 to cancel this exponential base 2 and get the perfect exact answer, log base 2 of 6. But now I want to also solve it using base 10 and base E and the generic base B. And I'm going to try to do that in all different colors. For this one, we are going to take log base 2 of both sides to kick the exponential base 2 out from underneath of the x. Don't write wide. Oh no, I wrote that 6 in red. That was supposed to be blue. This log base 2 and this exponential base 2 are canceled, and I have x equals log base 2 of 6. That is the perfect answer. No rounding involved, no calculator involved. There it is. But if you can think back to the top of this page, for example A, I told you log or ln, pick one, and we solved. We're going to use the common log because it is base 10. So I'm done with blue now. I am going to take the common log of both sides. Don't write wide. The common log does not cancel exponential base 2. However, there's an x in the exponent position here. Our expanding rules allow us to take this x to the front of this logarithm. We get x alone by dividing both sides by whatever number log of 2 is. But log of 2 is a number. You divide both sides. And you get x equals log of 6 divided by log of 2. Are you with me so far? We have solved using exponential base 2. We have solved using base 10. Log base 2, We solved using log base 2. We've solved using log base 10. Yes, Brock.
Why'd you take the 2 away from this one?
The 2 away? In green? Or in blue?
Aren't you supposed to log base 2?
That's what I did here. But here I'm solving using the common log. So this is base 10. Just like we did up here. So I just used log base 10 of both sides and expanded it to get the x out of the exponent position. See, I brought it out to the front. And that allows me to divide by whatever this number equals. Yes, Ilya?
So it didn't give you like log base 2. That's the way you solve it in green.
So this is how you would solve it using the common log. It's the same equation. This is me solving by hand using log base 2 to cancel exponential base 2. This is me solving by hand using the common log. See, my answer only has common logs in it. Okay. This one I want to solve using log base e, which is ln. So I'm going to take the ln of both sides. Don't write wide. The natural log does not cancel the exponential base 2. However, there is an x in an exponent position of my argument that allows me to expand, take this x, and bring it to the front of the logarithm. X times the ln of 2 equals the ln of 6. The ln of 2 is a number, so I can isolate this x with the division to cancel that multiplication. It gives me x equals the ln of 6 over the ln of 2. And then, lastly, and I would argue most profoundly, I'm going to solve using an unknown base, log base b of both sides. Really trying to hyper-exaggerate the curviness of my 6's so you don't think they're b's. Log base b does not cancel exponential base 2. But there is an exponent in the argument that can be brought to the front. Log base b of 2 would be a number if you knew what the base was, which means you could divide both sides by that number and isolate your x to give you log base, whatever base you want, of 6 divided by log base, whatever base you wanted, of 2. This equation has been solved 4 different ways. What does that tell you about those 4 answers? They're the same. All 4 of these answers are the same thing. They're just different formats. Here's base 2, here's base 10, here's base e. Pick a base, it doesn't matter, as long as you haven't broken the rules of the base. This is called the change of base formula. Here's the official change of base formula. This is how we evaluate log bases on our scientific calculator. If you want to know what log base 2 of 6 is on your scientific, you use log 6 divided by log 2. That is how you do it. You have to use change of base to use this calculator. And that's why every time I evaluated a logarithm for you, you saw me do it on my graphing calculator. Because I didn't want you to see the change of base formula yet. But there it is. The change of base formula is a very powerful thing. It allows us to write logarithms in any base we want. And then it allows us to do some really neat things that I'm not going to test you on unless it was extra credit. What do you say? But it's still really cool. Allow me to show you some things we can do with change of base. Let's say I've got something like, I don't know, this, where my log base is some ugly fraction. Ew, ugly fraction. And you didn't want it there. You didn't want the base to be 1 over b. Whatever would you do? You could use the change of base. Remember, base on bottom. Are you all comfortable with me saying that 1 over b is actually b to the negative 1 power? A couple people nodded their heads. Those people that hadn't packed up yet, that are still trying to get A's for the year, or are in general paying attention, there we go. This logarithm has an exponent in the argument position. Moves to the front. But when you have a negative sign on the bottom of the fraction, it's the same as if you had the negative sign on the top of the fraction. It's the same as if you'd had the negative sign in the front of the fraction. And then you could undo the change of base. Base on bottom. As it turns out, turning the base of the argument, or the base of the logarithm upside down is the same as reflecting over the x-axis. It's just a transformation. In fact, changing the base from any number to any other number will always be a vertical transformation if you use change of base to show it. Something else we could do right before the bell rings, because I'm a power nerd and I love my logarithms, is this. I would like to ask you, if I start with log base b of a, how is it related to this? What happens if I switch the base and the argument? Well, let's find out. Log base b of a using change of base is log of a over log of b. And log base a of b is log b over log a. What relationship do these two fractions have? Not inverses. Reciprocals. Here's what that tells me. Since they are reciprocals of one another, yeah, all these, they're walking to the door. Shoot, if they were my employees, I'd fire them. Your manager would understand that you hate the place and you're trying to escape? Yeah, well, anyway, that's pretty cool too. Thanks, people that were respectful enough to pay attention. Appreciate you.